record this. Okay, so generally in biochemistry as a whole, this subject, if you notice chapter 1, 2, 4 and 5, okay, is generally the chapters that you will need to always come back to, okay, when we go into the next chapters later on, when we observe, for example, carbohydrate and then carbohydrate metabolism or even lipid metabolism. If you been a bit lost with the terms or the reactions that occur within that metabolic reaction or process, you can always go back to these chapters, okay, especially this chapter enzyme, because a lot of biochemical reactions would be facilitated or catalyzed by enzymes. So if you feel that you have forgotten what's the role of enzymes, so you can always come back to these chapters, all right? Okay, so we have covered just now localization of enzymes. Now let's look into the mechanism of enzyme. So how does enzyme actually catalyze reactions? All right, so the first thing to understand is that enzyme has this tertiary quaternary structure, okay, so it have clefts or crevices, okay, meaning that it has a hole or space for something to bind to, okay. So this hole or place for something to bind is what we call as the active site, okay. So these active site are very highly specific, meaning it can recognize a particular substrate to bind to it, okay. It won't simply allow any substrate to bind, so only recognized or registered substrate can bind to this active site, okay. So okay, let's look into detail. Okay, so the mechanism of enzyme is generally from enzyme. So E is enzyme, S is substrate. Okay, so ES is the complex that will form, and then finally it will form back to enzyme, and P is product. Okay, meaning that, okay, we look into the mechanism later in diagrams. Okay, so this is what you need to know first. So from enzyme, it will bind with the substrate S and form a complex. A complex means a combination state where the two of it is bind together. So that's enzyme substrate complex. And finally, it will turn back into the substrate will be broken down, for example, or being ligated together into product, and the enzyme will remain the same. Okay, so this mechanism of enzyme is proposed to be happen in two theories. We have the lock and key model and also the induced feed model. Okay, so let's look into the lock and key model. So it's founded by Emil Fischer. So what does this theory propose is that the enzyme has it pre-shaped, and the active site has a rigid structure that is complementary to that specific substrate. Okay, meaning that, okay, enzyme will stay as it is. Okay, so this is the enzyme. So this is the enzyme has its pre-shape and it has already its active site. So this active site is rigid, meaning that it can only bind to a specific substrate. Okay, so the analogy for this lock and key model would be the enzyme is like the lock, mangga. Okay, and the substrate is like a key, kunci lah. Okay, so the substrate will fit into the active site in the same way how a key fits into a lock. So this is a rigid model, meaning that only a specific substrate can bind to the specific enzyme. Alright. For example, is like this. So this is a diagram. So imagine the substrate or the initial product is the key. The enzyme is the lock. So this is the lock key complex or the enzyme substrate complex. Okay. So in exams, if you are asked to explain the lock and key model, always explain how this key is, this lock and key represents enzyme. Okay, so don't only mention, okay, the key is being inserted into the lock and form lock key complex. So you would may only get half of the mark. So you have to mention, okay, the key represents the substrate, the lock represents the enzyme. Okay, and when lock key complex form is similar to enzyme substrate complex, for example. All right, so this is the model. So meaning that a substrate that has this structure can fit into this active site. Okay. So in lock and key model, again, using the same reaction, enzyme plus substrate equals to enzyme substrate complex. It will form this transition state first before it's being converted into product. So the first stage over here, first stage meaning this one. So reaction 1 and reaction 2. So the first stage here is reversible, and for some enzymes, the second stage is also reversible. Reversible meaning that after forming enzyme substrate complex, the substrate can decide to leave the enzyme and without changing the structure of the substrate. Okay, and in some cases, even after forming product, okay, the product can reverse its states back into a complex like this, or even back to its substrate form. Right? Okay, so once the product has been formed, it leaves the active site of the enzyme. So again, imagine this is the enzyme. So when substrate is bind, so after it's being, for example, let's take it, it's being broken into two. So now it will form product 1 and product 2. So it will leave the enzyme. Okay, so what will happen to the enzyme? The enzyme can be reused back to bind to another substrate that has the same active site, right? So enzyme will not change its features or structure. It can be reused back. So that is one of the properties of enzyme. It is reusable. Okay. Okay, so again, further details for lock and key theory. So imagine this is the substrate. This is the enzyme with the specific active site. So when this substrate the enzyme recognize the substrate that can fit into its active site, it will form enzyme substrate complex. So now, after binding, the substrate binding to the enzyme, it will catalyze the reaction accordingly, okay, depending on the enzyme. So now a product is formed. So after a new product is formed, the product will leave the enzyme, and the enzyme can be reused for another substrate to come in. All right. So that is for lock and key model. Another model is that induced fit model by Daniel E. Koshland. So this model is a bit flexible compared to the active site, the lock and key just now. So for lock and key is quite rigid, meaning that only substrate that can fit into the active site can bind to the enzyme. But for induced fit, it's kind of flexible, meaning that he proposed that the active sites of enzymes are flexible, not rigid. So meaning that the shapes of the active site can be modified to bind to the substrate. So it has a greater range of substrate specificity. Okay. So the substrate will induce the conformational change in the enzyme. Okay. Okay, for example, okay, this is the comparison. Okay, for lock and key model, it's directly like this. So meaning that the substrate needs to have the structure that can fit into the active site. But for induced fit model, the enzyme will adjust itself accordingly so that the substrate can bind. Okay, meaning that this is where what we call as the substrate will induce conformational changes in the enzyme. So when the substrate approach the enzyme, so it will induce conformational change to the enzyme so that the enzyme will now produce or arrange itself so that the substrate can bind to and form enzyme substrate complex. Okay, and finally form a product. And the enzyme may change back to its original state. Okay, so the difference of this lock and key and induced fit model is that for lock and key, we scientists have suggested, okay, for substrate A can only bind to enzyme A. Okay, but for induced fit model, enzyme A can bind to a wider range of substrate. Maybe for enzyme A, according to the induced fit model, enzyme A, it can bind to substrate A1, substrate A2, substrate A3. So it will adjust accordingly. So this substrate, they shouldn't be entirely different, but they may have a different side chain, for example. But they have similar structure between substrate A1, substrate A2, substrate A3. Okay, so because of that similarities that they share, they can share the same enzyme. Okay, that's suggesting that some enzyme could behave in a flexible manner. Okay, so we can take most of these theories actually, because some of the enzymes may behave like the lock and key model, while some enzyme may behave like the induced fit model, right? Okay, so that is for the mechanism of the enzyme. All right, so next is the enzyme kinetics. So after understanding how enzyme binds to its respective substrate, we need to know what are the factors that can affect the mechanism of enzyme. All right, so that knowledge is what we call as enzyme kinetics. Okay, the study of chemical reactions that are catalyzed by enzymes. So in enzyme kinetics, what is measured? The reaction rate. Okay, so in biochemistry, in science as a whole, when we talk about rate, it's usually related to time, how fast the reaction can take place. Okay, so reaction rate, meaning in enzyme kinetic, we will measure how fast or how slow a reaction would take place. Okay, the time taken, and the effects of varying conditions of the reactions. Okay, what are the effects that are changing or influencing the reaction rate? Okay, so the enzyme kinetics will reveal the catalytic mechanism of the enzyme, the role in metabolism, how its activity is controlled, or what drug or what are like a compound that might inhibit the enzyme. Okay. Okay, for example, I would like to share you some overview of why this enzyme kinetics is important. For example, nowadays people are taking supplements, kan, makan vitamins lah, and all those supplements lah. Maybe some may have been encountered with whitening product lah. So what's important for us to understand is whatever that we eat. For example, the supplements that we eat can affect the enzymes in our body. Okay, because some drugs or some supplements or vitamins that we are taking may affect the reaction rate of our enzymes. Okay, that's how it's giving impact to us. Okay, so that's example of the application of enzyme kinetics. So it's very dangerous if we take something or some supplements that can actually disrupt the activity of our enzyme. Okay, maybe the supplements are boosting the enzyme within our for example, muscle tissues, but those supplements are actually damaging the enzymes within our kidney. Okay, so that's why it's important for us to understand the enzyme kinetics. All right, so what the theory for us to understand enzyme kinetics is we will use this model, Michealis-Menten model. So this model will explain how an enzyme can cause kinetic rate enhancement of a reaction and why the rate of reaction depends on the concentration of enzyme presence. Okay, so in Michealis model of enzyme kinetics, the graph would be something like this. Okay, we will explain the reaction of enzyme based on the concentration or the amount of enzyme and also substrate that is formed. Product that is formed. Okay, for example, so in Michealis-Menten graph, usually it looks like this. So we have the graph, and then we have the enzyme. For example, it can be like this or like this, the reaction rate. Okay, and then we have, what we have more? Oh, substrate concentration. Okay, so over here would be substrate concentration. So after this, if I use this symbol, bracket like this is concentration, and this is the rate of reaction. All right, so this is the graph for this one, Michealis-Menten model. Okay, so let's look at this one by one. So at low concentration of substrate, so S is substrate, the initial velocity increase almost linearly with the substrate concentration. Okay, so this first sentence refer to this area. Okay, so at low concentration of substrate, okay, so this is the substrate concentration. So for example, let's take this is 0, this is 1 molar, 2 molar, 3 molar. So this is increasing concentration of substrate. Okay, so remember substrate is the initial product. So at low concentration, for example, from 0 to less than 1 over here, the initial velocity increase almost linearly. Okay, so the initial velocity refers to the rate of reaction. So at low substrate, the rate of reaction is linear to the substrate concentration. So what can we explain over here is that at low concentration, so as the substrate concentration increase, rate of reaction increase. Kan makin naik kan? So let's say this is the rate of reaction. Let's just put a number 1, 2, 3. So at concentration 0.1, maybe the rate of reaction is 1. At concentration 0.5, maybe the rate of reaction would be 2. Okay, so the relation is linear. They will increase together. Okay, so initial velocity again refers to the rate of reaction. Okay, for the second sentence, at higher substrate concentration, velocity increased by small amounts in response to increased substrate. Okay, now that we have increased substrate concentration increase, so this is this area. As you can see, the relation is not so linear compared to earlier ones. Okay, so this means that although the substrate reaction is increasing, the rate of reaction is not significantly increasing. Okay, maybe the substrate is changing from 0.1, for example, to 0.8, but the rate of reaction is only changing from 2.1 to 2.15, for example. Okay, that's what it means. Okay, there's an increase of substrate concentration, but the initial velocity only increase in small amounts. Okay, that is for sentence number 2. Okay, finally, a part is reached beyond which there are only negligible increase in velocity with increasing substrate. Okay, so finally we will reach to this state where although there is an increase of substrate concentration from 2 to 2.1, 2.2 to until 3, so there's increase of substrate concentration, but what can we observe in terms of the rate of reaction? The rate of reaction is stagnant. Okay, that's why we said that negligible increase. There's no increase at all. And this is where we call the state is at plateau. Plateau means stagnant. So at plateau, a maximum velocity is achieved, meaning the maximum rate of reaction is, the maximum velocity is increased, is achieved. Okay. So if you notice over here, how does this graph is being formulated is depending on the substrate concentration, meaning amount of substrate that we have, amount of initial product that we have, and it also depends on the amount of enzyme that we have. Okay, so the amount of enzyme is constant, okay, throughout this low, medium, and high. So let's look into the enzyme and also substrate diagram over here. Okay, so in low concentration, okay, enzyme ada berapa? 1, 2, 3. At medium ada 1, 2, 3. High 1, 2, 3. What's different in this is the concentration of substrate. So we have in low concentration, we have probably around 2, 4, 6 and 7. Okay, medium we have 2, 4, 6, 8, 10, 11. Okay, and higher has higher lah than 11 just now. So as the concentration of substrate increase, why does the rate of reaction does not increase? Why do you think so? Why at some moment it reached plateau, stagnant?
It's a maximum capacity.
Maximum capacity for, yes, for the enzyme. Very good. So the enzyme is at constant concentration. So although the substrate has increased, the enzyme has reached its maximum capacity. It cannot handle more. Okay, so it will only be stagnant or plateau. All right. So that is for enzyme kinetics. Okay, so this reaction or this diagram will be further analyzed, or they will derive a enzyme like this. So this is the formula. So Vmax is the maximum velocity where the reaction is at plateau, no more reaction. All right. So maximum velocity. We also have Km. So Km is the constant substrate concentration at which the reaction rate is half of its Vx. Okay, meaning that Vmax divide by 2, half of it, is where Km is. So Km will be the unit for Km is the substrate concentration. Okay, we will do the tutorial on how to use this formula later. Okay, just an overview first. All right, so these are the Michealis-Menten equation. So what are the factors that will affect this equation? Meaning that in certain condition, there will be different Vmax or maybe different Km constant. Okay, so what's determining all those differences is this: the temperature, pH, enzyme concentration, substrate concentration, activators, and also other factors. Okay, so factor number 1 would be in terms of its temperature and pH. Right, so what will happen in for temperature, for example, enzymes are most active at the optimum temperature. Okay, so for this part, you need to recognize the different graph style. Like for example, the graph for temperature is like this, pH is like this, okay, bell shape. For enzyme concentration is like this, substrate concentration is like this, and so on. Okay, so you need to recognize the graph differences. All right. So for temperature, initially, an increase in temperature will increase the enzyme activity until it reach an optimum temperature. So this is where the point where the temperature is optimum. So beyond optimum temperature, enzyme activity will drop. Okay, because the high heat that is present, for example, the high temperature will alter the shape of the enzyme. So when the shape of the enzyme is altered, it will change the active site. Remember, enzyme have an active site. So when the active site is altered, substrate cannot come and bind. Okay, so that's why the rate of reaction becomes low because it cannot bind to the substrate. Okay. So, and sometimes in extreme temperatures, enzyme can be denatured, meaning totally damaged lah, denatured. Okay, that is for temperature. So for pH is about the same. So pH for temperature is quite general for all enzymes. So at temperature, actually this should be 37. So 37 degrees Celsius is the optimum temperature for enzymes. That's why when people have fever, one of the quick or the immediate treatment that will be given by clinician is to reduce the fever, reduce the temperature. Okay, because before treating the causes of the disease, for example, okay, one of the main reason is because when our body temperature goes to an extreme temperature like 39 degrees Celsius, it will start to damage or disrupt or denature the enzymes inside our body, which can cause, for example, damage of certain organs, damage of certain tissues, right? Okay, so for temperature, so temperature is quite different, so it depends on the enzyme itself. Okay, so most enzymes are active at optimum temperature, optimum pH, for example, 7 to 8, around the neutral pH, but certain enzymes require acidic pH. Which enzyme do you think require acidic pH for them to function?
Oh, the gastric juice.
Yes.
Pepsin.
Yes, correct. So for example, the gastric juice or the digestive enzyme may require an acidic pH. Okay. So for certain enzymes, pH lower than the optimum one may slow the rate of reaction, but an extreme pH or pH beyond the optimum pH may denature the enzyme as well. Okay, because the structure of enzyme will change. When the structure of enzyme will change, active site will change. So when active site is changed, substrate cannot bind. All right. So the next factor would be the enzyme and also substrate concentration, or the amount of enzyme and the amount of substrate that we have. Okay, so the first graph would be rate of reaction against enzyme concentration, meaning the number of enzyme presence. So the reaction or this graph is linear, meaning that as the number of enzyme increase, the rate of reaction will increase because more substrates can bind to the enzyme. Right? So at a condition where the there is constant substrate concentration. Okay, meaning that the substrate concentration is kept at a constant rate, but we keep increasing the enzyme concentration, so we can observe there's a increase in rate of reaction. Okay, to visualize this, for example, we have in test tube 1, test tube 2, test tube 3. So in all of these test tube, we put the same amount of substrate. For example, 2 molar of substrate. 2 molar of substrate, 2 molar of substrate, but in each of the test tube, we put different concentration of enzyme. We have 1 molar of enzyme, for example, 2 molar of enzyme, let's use this E, and then 3 molar of enzyme. Okay, so what will we observe is that the rate of reaction, which one do you think will be the highest? In A, B, or C? Which one will have the highest rate of reaction?
The third one.
Third one, C, kan? Because it has the highest amount of enzyme.
Substrate.
Okay, the substrate is constant, so it has the highest amount of enzyme. So job can be done faster lah, basically. Okay, because the enzyme concentration is high. Okay. Okay, as for rate of reaction against substrate concentration. So just now is the amount of enzyme. So now we will keep constant the enzyme, but we will increase the amount of substrate. Okay, so this graph is actually similar to the first graph that we saw just now. All right, so as the amount of substrate increase, if we have the same amount of enzyme, eventually the rate of reaction will reach plateau or stagnant. Okay. All right. So this is a further detail of how enzyme actually catalyze the reaction. So we have an enzyme with its specific active site. So it will recognize its own substrate that can bind to it. And some enzymes may require the help or the addition of water. Okay, so to break the bond, for example. So now we have a new end product, which is, for example, over here is glucose and fructose. And the enzyme will, the product will leave the enzyme so that the enzyme can be reused for the next substrate. Okay, so enzyme, although they are themselves catalysts, but enzymes also require some support lah. So enzymes also have activators. Okay, for example, of activators are metallic cations. Metallic cations are, for example, magnesium, okay, zinc, copper, sodium. So these activators depends on the enzymes itself. It will act in a various way. So it will combine, for example, they can combine with the substrate, okay, or they can directly bind to the enzyme substrate complex. All right. So there are two categories of enzyme requiring metals for the activity. Okay, for example, the metal activated enzyme. Okay, so these metal activated enzyme are not tightly held by the enzyme and can be exchanged easily. Okay, meaning that, for example, the ATPase, they require magnesium and calcium, but this magnesium and calcium will not be permanently bind to the enzyme. Okay, they can bind and activate the enzyme, for example, and then leave the enzyme. Okay, we also have metalloenzyme. So what's different between metalloenzyme and this metal activated enzyme is that metalloenzyme can hold the metal tightly. Okay, meaning that they can permanently bind, or the bond between this enzyme or the metals are longer or tighter, okay, compared to the metal activated enzyme. Okay, so that's our activators. We also have coenzyme. Okay, so coenzymes are organic non-protein molecule. So if activators are usually metallica cations, but coenzymes are organic molecule that is required for the proper functioning of enzyme. So usually coenzymes are derived from vitamins, and these coenzymes, some of them can make up a part of the active site. Okay, so without the coenzyme, sometimes enzyme cannot function. Okay, for example, let me draw you again the enzyme structure. Okay, we have an enzyme, and then over here is, let's say, the active site. Okay, so within this active site, there's also a site for coenzyme to bind, apart from the substrate to bind. So some enzymes have this coenzyme binding site, where without the coenzyme, substrate cannot bind to its site. So maybe the coenzyme is like the initial door or the initial step before some substrate can bind. Okay, for example, we have NAD+. Okay, let's say we have substrate 1. So what will happen? So this is enzyme 1. Okay, so NAD+ will come and bind to its binding site, the coenzyme binding site on an enzyme. So upon binding of this NAD+, the enzyme will change its structure so that S1 can bind, substrate 1 can bind to the active site. So without this NAD+, enzyme will not change its structure. So the substrate cannot bind to the active site, for example. Okay, so this does not apply to all enzymes. So only certain enzymes have coenzymes. All right. So what are the other factors? So apart from pH, from the concentration, from the presence of coenzyme and maybe activators, what are the factors that are affecting enzyme activity? Is the product concentration. So sometimes the accumulation of product can actually reduce the enzyme reaction, and also light and radiation. Okay, exposure to UV, for example, can inactivate or disrupt or denature certain enzyme. Okay, that's why wear your sunscreen. Okay. Okay, let's take a 2 minutes break. I'll end the session and then come back in the same link. We come back at 12:25 lah. Boleh?
Okay, doctor.
Okay, let's come back 12 to